Hi, once again, this is Mr. Wakefield here, and we're looking at section 4.6, the last section of chapter 4. And we're finally going to get an opportunity to see how some of these things we've learned in chapter 4 are put to use in real-life situations. First of all, starting the topic right off the bat here is exponential growth and decay. In other words, when something grows exponentially or decays exponentially, what does that mean? We're going to learn the basics of that right now. Both of those situations use basically the same formula. The only difference is that this little k number, it's inside your exponent. When it grows, it's positive. When it's negative, it decays. All right. Now, just to get this out of the way as well, the word model in math is just referring to a formula. Okay, model is just basically another word for formula. In case you're wondering about that, I remember when I was a student, I was wondering what that word meant. It didn't seem like it fit into a math class, but the word model is just another word for formula, like I said. So, mathematical model, mathematical formula for exponential growth or decay is this right here. Now, it's got a lot of components to it, and so we're going to talk about each one. But before I tell you what each part means, as you can see here, we basically have 5 parts here. We got the y and the t, and then I highlighted the y with the little 0 underneath it. That's all one thing right there, y with the little 0 underneath it. That's one number. All right, they put the little 0 there to indicate that it's similar to this y over here, but it's the y at time 0. I'll explain what time 0 means coming up as well, but that's why they put the little 0 underneath it, but that's all one number there. Y0. They call it Y naught. All right. But it's Y sub 0. You could call it that as well. E, you already know what that is. We talked about that in the last few sections. It's a constant number. Your calculator will help you with that. You don't need to write down what that's equal to. We talked about that it was equal to approximately 2.71828, but you don't need to worry about that. Your calculator will take care of that for you. The K number is just basically a number that tells you how fast or slow it's growing. The bigger the number is, the faster it's growing. If it's small, it's not growing so fast. Same thing with decay. All right, if it's a small negative number close to 0, then it's decaying slowly. But if it's a bigger negative number like -2, -3, -4, if it gets bigger and bigger, all right, in the negative direction, then it decays quickly. So that's what those 3 things I highlighted there mean. The y and the t are the variables. All right, so let's look back at something that's similar to that back when we graphed the parabola problems in section 3.1. In those problems, in particular, this formula that we have, which is similar to this problem right here. In fact, I'll go ahead and look at this problem in particular. When you have it written like this, where you've got these constant numbers here, okay, some things in the formula are constants, all right? I highlighted that up here with the a, h, and k, but then the x and the f of x, otherwise known as x and y, because f of x is y, those things are the variables, all right? So you have some things that are constants, and each one of the constants has meaning. We talked about that over here, what the a, h, and k meant, all right? And then you have x and y, the variables. All right. In the same way, in the current formula that we're looking at, y and t are the variables. It's just like x and y. The only difference is that we call it t instead of x over here because t is going to represent the time. So it seemed like t would be a better letter to use, right? Okay, but it's the same thing as x and y. Just think of x as t now. That's all. So t and y are the variables. All right, you should have constant numbers in these 3 areas right here that I highlighted in green. E already is a constant, but the y naught and the k, those 2 numbers, you guys, those are the ones that we need to figure out what they're equal to. All right, just like we figured out in these problems, we figured out what h and k were equal to, and that became our vertex. We figured out what a was. That told us if the parabola went up or down. In the same way, we figure out what the y naught number is and the k number is. That then gives us a complete formula, and then the y and the t, they're part of the formula. All right, you don't figure out what those are equal to. All right, those are the variables. Those are the places where you plug in numbers, all right, in order to figure stuff out. But it's the green things here that are your constant numbers. They stay constant throughout the problem, all right, but the y and the t are your variables. So our goal on many of these problems is to figure out what the y naught and the k numbers are, so that we then have a formula where y and t are the only variables, and then just like here, where x and y were the only variables, you then could plug numbers into x to figure out what y is. And you can even, not that we did it here, but we could have, you could plug numbers into y to figure out what pairs up with it over here on the x side. All right. Remember we did that here. We plugged in x equal to 1, and we figured out that after solving the equation there, we found out that y was equal to -2. The function value is equal to -2. And so that's what you can do. You can do the same thing with t and y. All right, if you have a t right here and a y right there, you can then do that same thing, and we're going to do that on a lot of these problems. Okay, so a close connection between what we're talking about now and what we talked about with parabolas back in section 3.1. Now, what do these things mean? We talked about what those different constants meant, the a, h, and k letters. We knew what those meant with the parabolas. What do these things mean, the y naught and the k? Actually, I mentioned k already. I apologize. I already did mention that, but don't worry. I'll keep talking about it in case you're still trying to get used to that idea. So don't worry about that. But let me go ahead and, since we've talked about that already, let me go ahead and jump into the first problem here, and then we'll start to get used to those things. You can see it come to life here instead of me just talking about it. In all 5 of these problems, I want to make it clear right now, y, the letter y, we know that t represents time. We just talked about that. That's why they call it t instead of x. But what does the y mean? The y is the thing that either decays or grows. We're talking about decaying and growing, right? Exponentially. Well, what is that thing that's decaying or growing? In problem number 1, and just to talk about it in a general sense before I get into a specific problem here, usually when you're talking about decaying, usually it's some sort of like radioactive substance like plutonium. And then in problem 2 and 3, they just refer to a general radioactive substance here. They don't say exactly which one it is, but it is a radioactive substance. Okay, here they talk about, again, carbon-14, a radioactive substance. Okay, I don't know. Actually, I don't know if that's radioactive, but it is a substance. Okay, I don't think it is, but again, I'm a math teacher, so I'll leave that to other people. But it is a substance that what? It is going to be, what I do know about carbon-14 is it's something that decays over time, and so that's what's important. And in fact, it is something that decays exponentially, which is why we're talking about it here in problem number 4. That's what's important from a math perspective. And then on the back side, they talk about the population of a country, in this case, the population of the United States. And so that's something that actually usually, unless something severe happens, like a severe famine or something like that, where other than that, though, populations usually grow exponentially. All right. So let's go back to the front here. So those are the things that are radioactive substances or other substances like carbon-14, and then also populations. Those are the types of things that are going to be equal to y. Now, it says here 500 grams of plutonium-241 decays, so it's going to be a decay problem, according to this function. Let's stop right there. A of t, you guys, is because it has just a bracket with a variable in it and then just a letter on the outside of it, and that's all that it is, that's function notation. Okay, it doesn't have to be f of x or even g of x, all right, or something like that like we've seen in the past. All right, if you've got a parenthesis with just a variable in it, and then just a letter on the outside, and that's all there is on that side of the equal sign here. That's function notation. And as we know, you guys, function notation is equivalent to y. So you could think of this as y. You can even change it to y if you want. I'm okay with that. And then this 500, because of the fact that it's a constant number that's in front of the e right there, that is your y naught right there. All right? Because that's what the formula says, right? The formula says, in fact, I'll write it down up here at the top so I don't have to keep on flipping the page over. Y is equal to, again, the green pen here. Not that you have to use a green pen, but just highlighting the constant numbers here. Y naught EKT. All right? So since that's a number, since 500 is the number in front of E, that's going to be your 500 number. And then, as you can see there, since this decimal is being multiplied by T, that must be the K number, right? So 500 is equal to Y naught. Remember I said we need to figure out what the Y naught and the K numbers are, otherwise we're not going to get very far, okay? Sometimes they tell you what they're equal to in advance, but sometimes you got to figure them out. But we got to know them, otherwise we're not going to get very far with these problems, all right? So those are your two numbers right there. That's going to help us here. Again, they already told us that in advance, so I didn't really need to write this down. I already could see that K was equal to this and Y naught was equal to that. But since we're just learning it for the first time, I wanted to make sure you were seeing that, okay, when you look at the paper here. But let's start answering some questions here. Just like with the parabola problems, like I said, sometimes you're going to plug a number into one of the two variables, y or t, and then you're going to be asked to solve for the other variable. Just like what we did, like I said, when you plug a number into x and then you solve for y. It's that same idea, okay? But if you don't have a constant in the place of the y naught and the e and the k, then you ain't going to get very far. Fortunately, we do here, and so we can use this formula and start answering these questions. Now, since they say, let's read it here. It says, find the plutonium-241 remaining. Now, that's referring to Y, isn't it? Y is the actual thing that's either decaying or growing. Okay, so this must be what. So when they say find it, they're saying to find Y, aren't they? Because that's the substance, the radioactive substance. Okay? It says find Y after what? 4 years. 4 years, that's a time, right? So that must be the T, right? And so let's write this down. It says that we want to find Y when what? When T is equal to 4. Again, just like the parabola problems, we want to know what Y is equal to when X is equal to 1. Okay, what is Y when X is equal to 1? We plug it in to find out, and then we found out, and then those two things pair up. It doesn't mean we have to graph the current problems that we're doing. I'm just saying that this is how you find X and Y pairs. In the same way, this is how you find T and Y together. Okay, so if they say, hey, how much is left of the substance that's growing or decaying after a certain period of time, in this case 4 years, then that means you plug the number into T and then you solve for Y. And that's what you do. We're going to do that same thing here, same exact thing. It says find Y when what? When T is equal to 20. Okay, and so we'll do that. And then this last one's a little bit different. I'll get into that. Okay, first one, we plug T into the formula here, and you could say Y instead of the AT symbol there, all right? A little bit easier that way, but you could say A of T, that's fine. What's important is that you realize that whether you say Y or if you say A of T, you need to get you need to solve for that, and it's already by itself on one side of the equal sign, so you just got to figure out what the other side's equal to. Let me plug in that 4, and then you'll see that. So I plug in 4 right there, and as you can imagine, first of all, Y is by itself, so again, you just need to do order of operations over here to figure it out because there's no variables getting in the way now. Okay, I plugged a number into the T, and so I need my calculator, as you can imagine here, in order to figure that out. So let's go ahead and pull out our calculators right now. I'm going to look at both different types of calculators like I've done in the past to make sure everybody, hopefully everybody, and let me know if you're still struggling with your calculator use. But I'm going to look at both of the major types of calculators, the 2-line and then the 1-line as well. 2-line first. In order to figure this out, we're going to do order of operations here. So what is a negative 0.053? Remember, your negative sign is down here, you guys. It's not the minus sign. That's different. It's the negative sign. It's usually at the bottom of your calculator. All right. And we need to multiply that by 4, don't we? Remember, you guys, I should mention as well, you got to figure out what the exponent's equal to before you can take e to that power. All right. So when you have an exponent that has multiplication in it, for example, or any operation like addition or subtraction, you got to figure that out before you take e to that power. So there it is right there. That's the exponent. So here's what you do. If you have one of these calculators where the ANS feature is there, so here it says ANS down there again. I think we talked about that before, but I'll act as if we didn't, just in case. But I need to activate that. That means the previous answer will be then brought into the next part of the problem here on the calculator. So I want to take what? I want to take e to that power. So the first thing I need to do is I need to take e. I take the e to the x button. Again, this is on the 2-line calculator. The other calculator is going to be different. Hold on, I'll help you out with that if you're still waiting for that. But then it says e to what power? It's the previous answer. So see how it says ANS? That means your previous answer, it's going to take e to that power. That's what we want. Close up that bracket. All right. Like you always do. If the bracket opens, you got to close it. And then that right there is what e to that power is equal to. So I did the exponent on the inside of the exponent. Then I did the exponent itself by raising e to that power. And then we know that multiplication comes after exponents. And so I need to multiply by 500, and I get this right here. It says to round to the nearest whole number. That means to round to the nearest first this number that's closest to the decimal point on the left. Let me zoom in there a little bit for you. And so since the next number is less than 5, we're going to round that off to what? 404. 404 what, though? As we talked about before at the end of Chapter 3, when you have a word problem where it has measurement in it, and it talks about where's the measurement in this problem. It talks about grams right here. It doesn't just say 500, it says 500 grams, so that you know how plutonium is measured. It's measured in grams. When a problem has grams, typically, with rare exception, your answer should have measurement as well. So how is the 404 measured? Well, because of the fact that we figured out y, and y represented the thing that was decaying, which is the plutonium, then we know that this answer is in grams. And you got to say that. You don't need to make some big sentence like we do with a lot of word problems, like I've said before. I do need you to tell me how it's measured, though, okay, if the problem has measurement in it. All right, so since plutonium is measured as grams, and since y represents plutonium, then this number must be in grams as well. If you have a 1-line calculator, it's a little bit different. What you do is, it's only slightly different. What you do is, again, you still do order of operations in the same way. We have 0.53. You hit the negative. What I've noticed in 1-line calculators, you hit the negative sign after, not the subtraction again, but the negative button after that in order to make the number negative. You then multiply it by 4 again to get you to figure out what the exponent's equal to, just like we did on the other calculator. And then what you do is, this doesn't have one of those A and S keys on it, but that's okay because it has the EX key, and when you hit that, it will automatically take the number that was previously on the screen, this one right here, and it'll take e to that power. And that's what we want. We want to take e to that power right there. And so I hit the EX key. And as you can see, it gives you the same answer we had before we multiplied by 500, that is. And then when you multiply by 500, it gives you the same exact answer that the previous calculator did right here. Okay, same exact one. So 404. We're going to do exactly the same thing here in problem B. The only difference is that you plug in the 20, so this would be good practice right here. Same exact thing though, but it's always good to have some extra practice. So we plug in the 20, and then since y is already by itself and I want to figure out what it's equal to, I just need to take the other side of the equal sign and just stick that in my calculator and figure out what that whole thing's equal to. Okay, so let's go ahead and put that into the calculator. We got, again, 0.053 negative times 20. And then you raise e to that power. So on the one-line calculator, you just got to hit the EX button, and then it'll take that previous number that was on the screen to that power. Take it to the power of e. So that gives you the e part here. And then we multiply by 500 and we get that right there. So again, round that off to the nearest place here that's to the left of the decimal point. Since the next digit after the 3 is less than 5 right there, we are going to keep it as 3 and not round it up to 4. So this should be what? It should be 173 grams. So this stuff's decaying pretty slowly, huh? But it is decaying. All right, after 20 years, there's still a lot left. Okay, what does half-life mean? All right, half-life is the amount of time before, so they're asking for t here. They're not asking for y this time, they're asking for t. It's the amount of time before y becomes half of its original size. I shouldn't put it. This look like an English teacher right there. There's not shouldn't be a apostrophe there, but that's okay. We're not in an English class. Half of its original size. Okay. So again, this time they are asking for the t. All right. So we need to plug something into y this time and figure out t. In the previous two problems, we plugged something into t and we had to figure out y. Now it's the opposite. So you might be wondering, well, what do we plug into y then? Remember, y is going to become half of its original size. The original size is the size at time 0, okay, at t equal to 0, okay. But what is t equal to 0? That is the size at time 0 is the y naught number. And so, in other words, half of the y naught number, okay? Because that's the, you might be wondering, what do we mean by time 0? Well, it's whenever the 500 grams started decaying. That's what time 0 means, whenever it started decaying, okay? So whatever amount that they give you as your y naught number, when that starts decaying, that's time 0, all right? Now, since half of y naught, if you cut that in half, in other words, divided by 2, that would be what? That would be y equal to 250. 500 divided by 2. So that's the number that you plug in. Let's go ahead and do that. So I'm going to plug 250 into y, or at, same thing there. And then the rest of the formula stays the same. This time the the t is the variable this time. And so I need to solve for t right there. Okay, t is not by itself. How do we solve for that? Well, we learned about that in the last section, section 4.5. We learned that when you have a variable inside of the exponent, what you first of all do is you get the variable along with its base by itself. All right, and if it's not by itself, you do this little technique I showed you here where you get you pretend like it's a variable, and then you do the same thing you normally would with the variable there. You get it by itself, and then you do that thing where you put the ln on both sides, and we'll go from there. All right. So let's go ahead and do that. Since the e is the base right here, you guys, and the 500 is not included in the base in the exponent right there, what we need to then do is we need to pretend like this is 500 times y. If it was 500 times y, just like I pretended like this red box was a variable right here with the base and the exponent in it, okay, pretend like the base and the exponent here is a red box, pretend like that's a y right there, 500 times y now, okay, what would we do in that case? We would divide by the 500, wouldn't we? Because that's just a normal looking linear equation up there. So in the same way, we would divide by 500 here. Okay, and what is go ahead and make that into a decimal as long as it's not one of those decimals that covers your entire calculator screen, because we don't want to round off before the final answer if we can help it. Sometimes we can't help it, we'll get into that, but if we can, we shouldn't round off before the final answer, and we shouldn't even round off in the final answer unless we're told to normally. Okay. What is 200 divided by 250 divided by 500? It is 0.5 in your calculator. That's a nice little decimal. It was not rounded off. If it was rounded off, your calculator, unless your calculator is in a weird mode, and I could talk to you about that if you're not getting the same answers here. But if your calculator gives you a decimal that does not cover the entire screen, all right, that means they didn't round it off. It's exact, and that's a good thing. Once we get the base and exponent by itself, what do? We take ln of both sides. Ln of both sides. And as we learned in that same section, when you have ln of e to a power, what happens is that when you move the exponent to the front, in this case x to the fourth, the ln of e then just cancels because ln of e is equal to 1. And so you're just multiplying by 1. And so it's the same idea here, where you move the exponent to the front here, and then the ln e cancels out because ln of e is 1. And so it's just like doing this this term right here times 1. You can cancel that out. And so we end up with ln of 0.5, and then just like this problem here, actually it's not exactly like that problem, excuse me, because it has x to the fourth. This just has t, it's not t to the fourth or something like that. But remember, if you have no variable on one side of your equal sign, no variable, and then over here you have a constant times just t to the first power, key thing there is t to the first power, then it's just a normal linear equation where you divide out, because it's t to the first, all right, and you get t by itself. You just need to put this in your calculator now and figure out what t is equal to. I did not put how to round that off. I apologize. All right. I would if it was a test question so that there's no confusion. But go ahead and round this off to the nearest year. Okay, and as you can see here in the problem, the year, the t already is measured in years. So if you round off to the nearest year, that means again just to round off to the nearest whole number. All right. So let's get it on the calculator screen, and then we'll talk about that. We did something similar to this when we had our previous problems, where we had. You know what? Actually, we didn't. Okay, but we'll go through it carefully here. I just want to make sure you're entering it carefully and correctly, of course. When you have just an ln on the top of your fraction and then just a normal number on the bottom, what you do is you enter your ln like you normally would. Okay, everybody's calculator is different, but I'm assuming by now you know how to enter the ln's based on previous sections. Just do that. Figure out, get that on the screen there. And then after you do that, then hit divided by, keep that on the screen, and then hit divided by, and then divide by this. Don't forget the negative there, though. Divide by the, and then just enter that negative decimal the same way you normally would. And it gives you this right here. Now you can see here that the next number after the 3 right there, since we're rounding to the nearest whole number, since that's less than 5, it's going to be 13. So t is approximately equal to 13. 13 what, though? 13, remember, t is measured in years in this problem. And so again, we got to put our measurement in there. Don't just say 13. And so the half-life, in other words, the amount of time it takes to go down to half of its original size, is 13 years. Okay? Moving on here to problem number 2. Let's read it here. It says 10 grams of a radioactive substance are present initially, meaning at time 0, and that's why they say that y sub 0 is 10, because it's at time 0. The word initially implies that, time 0. And 3 years later, only 5 grams of it remains. How much will be present after 8 years? And we'll get into that question here in a second, but let's set some things up here first. Notice, and we saw this kind of thing when we were graphing lines before, where they give us 2 different data points. When I mean by data points is I mean points like points on a graph. Not that we're going to be graphing, but it's similar to that, where instead of x and y, we now have t and y. All right. Notice that it says that at time 0, the radioactive substance, which is y again, just like in the last problem, that's 10. So 0 and 10 go together. And then 3 years later, so y is equal to 3 here. Pardon me, t is equal to 3 because years is time. In 3 years, you're going to have 5 of the substance, so y is equal to 5 there. You can, when you get 2 data points like that, you can actually build your own formula, all right, from scratch. And let me show you how to do that, because once you do that, then you can just simply plug 8 into t here in order to figure out this question. But you got to have a formula to plug into. They didn't give us one, so we got to build our own this time. So that's what you do if they give you 2 data points. In other words, a t and a y that go together, 0 and 10, and then another thing where the t and a y goes together, the 3 years and the 5 grams. All right, this is how you do it. First of all, if one of your data points, and one of them has to be 0, otherwise this isn't going to work, but one of them is t equal to 0, so that automatically tells you what the y naught number is. Remember, in order to build your own formula, you got to be able to figure out what the y naught is and what the k is. So because you already know that 0 pairs up with 10, you know that y naught is 10. Even if I hadn't told you this in the question, you still would know that. So that's what you do. You take the when t is equal to 0, and that becomes whatever y that pairs up with it. That's the y naught number. So what we have now is we have this. We have y equal to 10 e, and then I just have to figure out what the k is right here that pairs up with the t right there. So that's the missing part that I still need to fill in right there. We're going to do that right now. How do we do that? Well, now that I know what the t or what the y naught is, so make sure to plug that in first, because we're going to need that in order to do the k part. But plug that in first, and then what you do is you plug in the 3 and the 5 into the y and the t, not permanently, that's not part of the formula, but it's just for the purpose of solving for the missing part here, which is k. I'll go ahead and put the k in there right now since I don't know what it's equal to yet, but eventually I'll change it once I figure out what the k is equal to. So what you do is you plug in the 5 into the y and the 3 into the t, and then notice that k is the only letter left in the problem, right? If you have only one letter, I don't want to call it a variable because it's not really a variable, but it acts like one because it's a letter. But you only have one. When you have only one letter left in the equation, you can typically get it by itself and solve for it normally. All right, and this is no exception here. So how do we do that? Remember we said that if you have a variable in your exponent, you first of all want to get the base and the exponent by themselves. All right. So this is just like 5 equal to 10 times y, just like what I talked about up here with the half-life problem. You then divide out by the 10, just like I divided by the 500 up here. Then we get 0.5 again. Just a coincidence that it's equal to that. It's not always going to be equal to 0.5. But and then we have left over here e to the 3k power. K times 3 is 3k. Then we do what? Then we, just like in the half-life problem and just like we did in 4.5 on a lot of those problems, After you get the base and the exponent with the variable in it by itself, then you take the ln of both sides. You then move the exponent to the front of the ln. Okay, the one that had the variable in it, you move that exponent to the front. Okay, and you're only allowed to do that, you're only able to do that if you, first of all, divide out the 10. Okay, so don't forget to divide out that 10 first to get the base and the exponent by itself. But remember, ln of e is equal to 1. 3k times 1 is just 3k, and so that's why I just canceled out the ln e. It just ends up not contributing anything to the problem because you're multiplying by 1, just like we talked about in the last problem. Once again, I now have a no variable over here. If you have no variable over here and then you have a constant times k to the first power, key thing there is k to the first power, then it's just like a normal linear situation where you divide out in order to get the k by itself. And then you could see that this answer looks very similar to this answer right here. The only difference is that you have a 3 on the bottom instead of a decimal. So enter it into your calculator exactly the same way we entered this, okay? And then what we end up getting is k is approximately, and you can round it off to the 3 decimal places. All right, I know I didn't mention that here because it's not the final answer, but yeah, I'm okay with you rounding off k's. Okay, if you get, in fact, I'll put that in your calculator so you can see what I'm talking about here. ln 0.5 divided by 3. I'm going to round off the 3 decimal places to the right of the decimal point. So it's negative 0.231. I'm okay with you, like I said, rounding off k's because usually the k's are going to be those nasty decimals that cover your entire calculator screen. There's no way to get an exact k, all right, unless you leave it in fraction form over here. We're not going to do that, okay, because that's just going to make the next step a lot tougher. So I'm okay with you rounding off k's if it's a big, huge decimal on your calculator, just like I'm okay with you rounding off an x or y value that goes on an xy graph, okay, like we talked about before. And so we now have the k. What's the formula going to be now? The formula, now that I know what the y naught is and I know what the k is, it's going to be y equal to 10 e to the negative 0.0, pardon me, the zero's on the, it's not on that side of the decimal, excuse me. You could say negative 0.231, or you could just say negative 0.231. Remember, if there's a 0 and only a 0 on the left of the decimal point, that does not need to be written, okay, although you could write it if you want. Don't forget the t after that. So remember, in order to have a full and complete formula for these problems, exponential growth and decay, you've got to have a constant here, and you've got to have a constant here next to the t in the exponent. We do now. And so now I can answer any question they throw at me now, okay, including this one. It says after 8 years, what does that mean? It means find y when, just like in the last problem up above, find y when t is equal to 8. Okay? And so let's do that. I'm going to plug in t equal to 8. That. And then we just have to figure out what this is equal to the same way we did up here. It's exactly the same setup. You got to figure out the decimal first, or pardon me, figure out the exponent first, and then take e to that power, and then multiply by 10 this time. If you do that, and it says round to 2 decimal places, if you round to 2 decimal places, we get 1.58. 1.58 on our calculator. But it's 1.58 what though? 1.58, again, Y is the radioactive substance. How is the radioactive substance measured? It's measured once again in grams, G for grams. You can say G for short if you want, like that. And there you go. So that's how much of that radioactive substance is still left after 8 years. Okay. All right, next. If you have a radioactive substance with Y not equal to 20 milligrams, and the half-life is 200 days, then assuming that this models the situation, in other words, like it typically does with a radioactive substance, this exponential decay formula, assuming that that is the correct formula, that's what they mean when they say models the situation. It means it's the correct formula, okay, for this situation. Then in that case, find the value of K. All right. So it's kind of similar to the last problem, only kind of a shorter problem, actually. They told us that Y naught was 20, right? So we're going to get Y, and then I replace the Y naught with the 20. Okay, bring that down here. And then they want to know what the K number is. Okay. How do I figure that out? It's kind of similar to what we had over here, where when they say half-life is 20 days, you guys, let's talk about that. That means that T is equal to 200 when Y is equal to what? Okay, well, remember, half-life is the amount of time, in this case 200, for Y to get to half of its original size. Well, its original size was 20. I know that because it has the Y0 right here. That means the original size at time 0. And so just like up there here where I cut the 500 in half in this problem, okay, and then the Y for the half-life was 250. In the same way, I cut the 20 in half, and so now the Y is now 10. So that means that 200 pairs up with 10 because it takes 200 days in order for the Y to get to half of its original size. All right, which is 10 because it's half of 20. Anyway, so just like in the last problem, now that I have a pair that go together, okay, the 200 occurs at the same time that 10 occurs, 200 days for 10 milligrams, pardon me, then we can, since those two numbers go together, it's like an ordered pair on a graph, all right? You can then plug them in together into the equation at the same time, and it's a perfectly valid thing to do that. It makes the equation true. Okay, like with any ordered pair, if they go together, if they are an ordered pair and they occur simultaneously, you can plug them both into the equation at the same time, and it's perfectly valid to do that. It makes the equation true. All right, so what do we get? We get 10 and 200 plugged in to their appropriate places, and then just like in the last problem, what that means is that K is the only variable left, just like it was up here after I plugged in the 3 and the 5. And so we do exactly the same thing. We've got to divide out the 20 in order to get what? In order to get the base and the exponent that has a variable in it by itself. All right. And so once again, we get 0.5. Yeah, that's a very common thing because we've been talking about half-life a lot. But again, that's not always going to be 0.5. We then take ln of both sides. Okay. And once again, the side that has the variable in it, you move the exponent because it's in the variable's in the exponent. You move the variable, you move the exponent to the front like we always do. That cancels out the ln of e because it's 200k times 1. All right. And then just like in the previous couple problems here, you then divide by the 200 in order to get the k by itself for the same reason as we did it before. All right, if you put that into your calculator right now, it's going to end up being what? And again, you can round off the k to 3 decimal places. Again, I'm okay with that. There's no way of getting an exact answer. Let's go ahead and put that on our calculator here. I'll use the one-line one this time. Remember with ln or log, you put the product term in first, and then you hit the ln. That gives you what the numerator is equal to right there, and then you divide by 200. And if you round that off to 3 decimal places, the next digit, the 4th decimal place, is less than 5 right here. So that means that negative 0.003 is the answer. So K is approximately equal to negative 0.003. Again, you don't need to write that first 0 right there because it's the only digit on the left side of the equal sign. And if it's 0, then you don't need to write it. But either way, you do need to write the other zeros, though, because they're on the other side. And so that's K. That's all they wanted you to know there. That's all they wanted you to figure out. All right. Next one here is a little bit different, but a lot of similarities as well. It says, a sample from a refuge deposit near the Strait of Magellan, okay, which is... I should know my geography. I think the Strait of Magellan is way up north. It's a body of water that. Anyway, we don't need to talk about geography. The point is that they found this sample and it says it has 60% of the carbon-14 of a contemporary living sample. In other words, it has 60% of the original amount of carbon-14 that was in a living being, okay, whether it's we don't know if it's a human being, an animal, whatever it may be, but based on the fact that there's 60% left, you can actually figure out how old that sample is. And let me show you how to do that. Okay. What they're saying here is that they're saying that the actual amount of the substance, which is Y, as you guys know, okay, they're saying that Y is, in other words, Y equals 60% of the original amount. Okay, and I know it's original amount because a living being, when it's still alive, all right, it still has all of its original carbon-14. It's when it dies that their carbon-14 starts to decay off. And so when they say living, they're referring to Y naught right there, the actual amount at time 0 before it starts decaying, because it's still alive, it hasn't died yet. Here's how it works though. 60% of, whenever you put the word of after 60%, that means, first of all, you got to convert percentages. You can't use percentages in equations. You've got to convert it to either a fraction or a decimal. 60% means 60 divided by 100. Percent symbols always mean divided by 100. So 60 divided by 100, if you put that in your calculator, converting that to a decimal, because it's easier than a fraction, is 0.60. 0.60. Since the word of is after the percentage, that means multiplication. So Y, in this case, the Y that they want us to use is 60% of the original amount, so 60% of the Y naught. So what they want us to do, just like in a lot of these problems, is they tell us what the Y value is, and then they want us to figure out T. How do I know they want to figure out T? It's because how old is a reference to time, isn't it? Okay, when somebody asks you how old are you, you're going to tell them how many years you've been alive, right? It's time. And so, just like normal, if they give you the Y and you want to figure out T, what you do is you plug in the Y into, and I know it looks unusual because there's a variable there. It's not really a variable, it's Y naught, but we don't know what it's equal to. But don't worry, we're still going to be able to do it. I'll show you why. It's a little bit different. Okay, and you know what? And don't worry, I would not make you memorize something like this. But the carbon-14, just like all radioactive substances, they all have their own K number. And so I need to tell you what that is. All right, it is... I knew there was something wrong there when I put that in there and we didn't know what the K was. Almost forgot to mention that. Don't worry, if this was a test question, I would tell you what the K number was here, because there's no other way that you would figure it out unless you knew what the K was in your own brain. And I do expect you to memorize and remember things in a lot of other areas, but not with this. All right, I would actually give you this. Knowing what this number is not important for mathematical purposes, so I would give you that. If this type of problem, for example, showed up on a test question, all right. But again, I'm just talking about K numbers that we aren't capable of figuring out already, and we wouldn't be here, all right. So if there's a K number for a radioactive substance and there's no other way of figuring it out on your own on the test question, okay, such as this problem here, then I would give that to you if you need it, if the K number is needed, and it will be needed here. Okay, what do? Again, we want to figure out what T is equal to, because it says how old. So again, that means the variable. I know Y naught looks like a variable also, but as you're going to see here, it's not. It looks like one, but it's going to end up canceling out here. Why does it end up canceling out? Well, when you've got your variable and your exponent, and you need to get the base and the exponent by itself first, right? Well, when I divide both sides by Y naught, and I divide by Y naught for the same reason why I divided by 20 up here, you got to get the red box by itself. If I do that, the Y naughts cancel on both sides here. Okay, they cancel. And so even though we didn't know what Y naught was equal to, it wasn't important because it canceled out anyway. Sometimes that kind of thing happens. It's real nice, all right, because then you don't need to worry about knowing it. So we end up with that. So now it looks just like the last few problems here. You got a constant on one side. You got a base and an exponent on the other. We do the ln of both sides. You're going to have that thing again where you move the exponent to the front, and then the ln will cancel out. Okay. Let me write that down like this. The other side's still the same for the moment. Okay. Move the exponent to the front. The ln of e cancels out because it's equal to 1. And then just like we've talked about on the last few problems, if you have no variable on one side of your equal sign and then the other side is a constant times t to the first power, okay, you can just divide out to get the t by itself. All right, so if I take this and I put it into my calculator, all right, very similar to a lot of the problems we've already done as far as how you put it in your calculator. You just have an ln divided by a decimal. If I put that into my calculator right now, I am going to get the following here. It's going to be 4,201 if you round it to the nearest year. Okay. And when they use this K number, by the way, the T is measured in years. That's the only way that it would work, is if it was. And so since you get 4,201 rounded off in your calculator, if you put this in there, round it up to the nearest whole number, that is. Let's go ahead and take a look at that. We'll just put it up on the screen here so we can talk about it more easily. So we got what, 0.6 ln. There it is right there. And we're going to divide by this big, huge decimal. Don't forget to make it negative. Okay. There you go. And you can see that because the next digit after the decimal point is greater than 5, it's going to round up to 4,201. All right. That's the nearest whole number. So t is approximately equal to that. That means that that living animal, whoever it is, okay, that living being, it's been dead for 4,201 years, okay? That's how old the sample is at the time that they found it, and they tested it out and everything, and they found out that there was still 60% carbon-14 left. Okay, it had been there for 4,201 years. That living being had been dead that long. Okay. Flipping over to the back. Like I said, now we're going to talk about population. So for the first time, I'm going to be talking about exponential growth. The only difference is that now the K is going to be positive. All right, but once again, just like in problem number 2 over here, it gives us 2 data points. Again, here we had a T matching up with a Y, a 0 and a 10, and then we had a 3 matching up with a 5, a T and a Y there as well. The same thing happens on this problem, and that's good because we're going to need to build our own formula here. Again, you can see that there's no formula here, is there? Okay, so we need to build our own formula so that I can then answer the question. I'll know what to plug into and all that. So let me make my little chart here. Okay. Something that they don't point out to you, though, that I do need to point out to you is that when they do give you 2 data points, and you can see here that 1990 pairs up with 250 million, and you can see that 2000 pairs up with 280 million. This time we're not given any clues on what time 0 is. All right. So we need to, since we're building our own formula, we can do it however we want, really. Okay, unlike problem number 2 where they told us that the 10 was at time 0. All right, they don't tell us what time 0 is this time, so we got to decide what that is on our own. Usually what you do when that happens, if they give you 2 data points and they don't tell you which one was time 0, you just pick the earlier time. See how we got 1990 and 2000? So 1990 can be your earlier time. Okay, so this is how it works. If that's time 0 right there, then what is 2000? Wouldn't that be 10 if you measured in years like we oftentimes do? We don't always do that, but it is talking about years here, so we should do it that way in this problem. Okay. So since this is 10 years later, this would be t equal to 10 if you made that t equal to 0. So again, you can do time 0 however you want, but you're going to want to have time 0 in your problem, though. So you want it to be one of these 2 things. Remember I said you can't build the formula very easily, if at all. It's definitely a lot harder to try to do it. It can actually be done, but it'd be a lot harder if you don't have the time 0. We mentioned that in the problem number 2. So if they don't tell you what it is, just pick the earlier moment in time. And then the other one, you just count the number of years after that. And so we got 0 pairing up with 250. You don't need to say millions right there, okay? And I'll show you why here coming up. You'll notice that all the numbers, all the population numbers in the problem are already in millions. They even say round to the nearest million. So you can't always do this, all right? But in this particular type of formula, as long as the y and the y naught numbers are both measured the same way, in other words, if one of them's in millions, like this one is, and the other one is in, if both y and y naught are already measured in millions, then you don't have to write down the 6 additional zeros. You know, like 250 million, you have 6 zeros after this, don't you? You don't have to do that as long as you establish that the y and the y naught are both going to already be measured in millions. All right, I'll get into that more here as we go along. But if it's already understood that both of these 2 things right here are in millions, then you're still going to get the right answers without having to put those 6 additional zeros behind the 250 and the 280 right here. Speaking of the 280 pairs up with t equal to 10, doesn't it? So just like in the problem on the front, we have 2 data points, one of them with t equal to 0, the other one not. But those 2 things will help you figure out what the y naught and the k numbers are so that you then have a full and complete exponential growth formula, exponential growth model as we call it, so that you can then answer the question that they gave you. Okay? All right, so what we need to do first is, like we did in problem number 2, realize that because 0 pairs up with 250, that must mean that y naught is equal to 250. Please establish that first, that y naught is equal to that, because you're going to need to plug it into the formula, this formula up here, in order to figure out what the k is. All right? And so now, just like we did with that 3, 5 data point in problem number 2, I'm going to take this point right here that does not have the 0 in it, and I'm going to plug that into the formula along with the 250 that I already established, and I get what? I get, in fact, you know what? Actually, excuse me. Before I do that, just like I did in problem number 2, just to make it clear, okay, what we're trying to do here, we now know that this number is 250, and so just to explain it one more time here, if I plug 2 numbers for t and y into these 2 spots right here that go together, and we know that 10 and 280 go together, then I can then realize that k is the only variable or the only letter left, and so I can solve for it. I can get it by itself. Okay, there won't be any other. See, you can't get k by itself right now and expect to know what it's equal to, because if you do, then you're going to end up with variables on the other side of the equal sign, and then you won't know what it's truly equal to, right? But if you, if k is the only letter left in the formula, then if you get it by itself, it should have just an actual number on the other side, no variables there, and then you'll truly know what k is equal to. So let's plug this thing in now. We plug in 280. And we plug in the 10 into the t spot. And then, just like in problem number 2, we then have k as the only thing left over. Again, I have to do what? I have to get, in order to figure out what k is equal to, I got to get this by itself first. All right. What is 280 divided by 250 in your calculator? Let's figure that out. Okay, because again, it's easier to use a decimal as long as it's not one of those rounded off ones. 1.12, that's not rounded off because it doesn't take up your whole calculator screen here. So that'll be much easier to use instead of keeping it in fraction form. Okay, actually make it into a decimal. We then do the same thing we've been doing, which is after you get the red box by itself, you then take the ln of both sides. We then move the 10k to the front. The ln of e then cancels out because it's equal to 1. And then once again we have no variable on this side, and then we have a constant times k to the first on this side. We've seen that many times now. All right, you can divide out to get the k by itself, and it is equal to what? Let's find out. If you put that in your calculator right now, ln of 1.12 divided by 10, and there is your k number. Again, you can round your k numbers off to 3 decimal places. So the next digit here, since it's less than 5, it's going to stay as 0.011. The 1 doesn't bump up to 2. It stays as a 1 right there, that second 1 right there. So notice that the k number is positive this time. This is not a surprise because this population is growing, not decaying. Okay, so you don't have to put the squiggly equal sign here, but I just like to do that to indicate that we rounded it off. It's approximate, it's not exact. So what do we got now? Now that I know what the k is and I know what the y is, I now have a fully operational formula here. It is y equal to 250 e to the, and then you put the k number in there, with or without the 0 in front, it doesn't matter. And there is your formula right there. Once you have a formula with the y naught and the k established in there, and t and y are the only variables left, you can answer any question regarding the year or what time something happened or how much of the population is left. You can do any of that kind of stuff. In this case, they say what year, which means what, you guys? That means t, doesn't it? They want to know what is t, because t is referring to time, and year. When they say what year, they're talking about time, right? What is t when what? Well, it says what year will the population be 400 million? Since the y already is in millions, as we established, okay, we already said that we're going to make our y and y naught in millions. That's why I wrote down 250 here instead of 250 with a bunch of zeros after it. That means that the y for 400 million is just simply 400. You don't need to write down the 6 additional zeros behind that like you normally would if it was the entire number written out. So what do we do when they ask for t and they give us a y that's supposed to pair up with it? We just simply plug in the 400, okay. Oh, you know what? I skipped a question there, but that's okay. I'll come back to it. We're supposed to estimate the U.S. population in 2020. I'll come back to that. All right. Excuse me for if that threw you off there. Let's answer this question first. We do have a couple questions though in this problem. Okay, so again, I need to divide out by the 250 in order to get the base and the exponent by itself. Again, you do that when the variable's in the exponent. Okay, 400 divided by 250 is equal to exactly 1.6. And so let's use the decimal equivalent there. It's better than using the fraction. Okay, some people may want to just reduce that to lowest terms right there, but it's better to do the decimal. It's easier. Again, we take the ln of both sides. Okay. We then have this thing where we move, like we've done so many times now on this sheet, we move the exponent to the front. The ln of e cancels. We have just an ln on the other side, no variable over there. So once again, for the same reasons as before, I can divide by the thing that's being multiplied by the t in order to get the t by itself. Like that. So what's this equal to over here on the left-hand side? This is equal to, if you put that in your calculator, it's going to be approximately, if you round it off, it says round to the nearest year. And since we're already, notice that we already have t in years here, okay? 0 years and then 10 years later in the year 2000. So t is already measured in years. So if they want to know the nearest year, you just do the nearest whole number then. Okay. That's what that means. If something's already measured in years and they say nearest year, that means nearest whole number. If you put that in your calculator, nearest whole number, in other words, the nearest number on the left of the decimal point, that's where you're rounding off to. That's going to be, just like we did before in a lot of these problems, it's going to be approximately 43. Okay, now that's not your answer. It's not year 43, right? That's almost 2,000 years ago. That's not what we're talking about, right? No, we're talking about 43 what? Well, remember, when was time 0? What was time 0? Time 0 was 1990. 2000 was time 10, right? So what would time 43 be? Okay, well, because the reason why 2000 is time 10 is because it's 10 years after 1990. So in a similar way, this should be what? This should be 43 years after whatever time 0 was, which was 1990. Okay, so if t had been 50, for example, then you would measure 50 years after 1990, because again, 1990 is when the time began for the sake of the formula. Okay, it's when time is equal to 0. Don't just leave it like that. Actually add that up for me, okay? What is 43 years after 1990? We just simply add 43 to 1990, don't we? And so the year would be 2033. Okay, so based on this formula, which is not necessarily accurate, as well as you'll find out more about here in just a moment, but that's up to statisticians and people that work for the government and everything like that in order to make sure that the formulas are correct. All right, I'm not sure where this actually came from our textbook, I believe, if I remember right. So I don't know where they got it from. It's not necessarily accurate, but you hope that people that actually do this for real, for a living, that it is accurate. Right now, we're just learning the mathematical side of it and how it works. All right, but yeah, hopefully it's accurate. But as you're going to see here, as I now estimate the population in 2020, And since I'm doing this video in the year 2020, okay, we can actually figure out if this next answer is accurate or not. Okay, that kind of makes it interesting. All right, so let's do that. It says estimate the U.S. population in the year 2020. So what are they asking for here? They're saying that they want to figure out the population. Remember, population is Y, right? Population is Y, just like the radioactive substance was Y. It's the thing that's growing as opposed to decaying. But whether it's growth or decay, all right, in this section here where we talk about exponential growth and decay, that is going to be your Y. And so what they want to know right here is what? They want to know what is Y? What is Y? When what? When we're in the year 2020. But I don't plug in 2020, you guys. Remember, T does not represent the year, you guys. It represents the number of years after 1990. That's why T was not equal to 1990 right here. It was equal to 0. This is why T is equal to 10 over here instead of 2000. So what would it be in 2020? Well, isn't 2020 30 years after 1990? And that's the reason why we designate T to be equal to 30 for the year 2020. That's the number you got to plug in order to get the correct answer. Let's do that. So I'm going to plug in into the formula, the one that I established up here, okay, which you can use on all the questions now in this problem that they ask you. It says, what is Y when T is equal to 30? So I'll plug the 30 into the T. And then since Y is already by itself, this is just like the very first problem that we did where you plug a number into T, the Y is already by itself. So you just got to do order of operations over here on the right-hand side of the equal sign. You don't need to like divide out or any of that kind of stuff. Just do the same thing we did in the very first problem with the plutonium. Okay, what do? We do the exponent first, right? There's your exponent. We take e to that power. Okay, and then we multiply by 250. And we get this right here. It says round to the nearest million people. Since the Y is already in millions, that means the nearest whole number again. So, since the next digit after the nearest whole number is greater than 5 right here, that second 7 right there, that means that this first 7 is going to bump up to 348. 348. So that's going to be approximately 348. How do we measure? Remember, we got to put our measurement in our answer. Okay. Here, I know it seems like I didn't do that. You could say the year 2033, but if you say 2033, I'll already know that you're talking about the year. So, but you could say that in order to be consistent with what we've been talking about and say how it's measured and all that. That's okay though. You don't have to write down you don't have to say the word year. I already know that that's what you're talking about. But how is Y measured though? Y, because it's population, it's measured not just with people. You don't just say 348 people, right? Of course not, all right? The U.S. is way bigger than that. No, it's measured in millions like we talked about, right? Measured. So any Y value or a Y naught value that you get will already be in millions. And so 348 is not just people, it's million people. 348 million people. Okay. So what is the actual population in the year 2020? There it is right there. So it's a little bit off, isn't it? Okay. Not 2010 here. That was a comparison that they were talking about there. In fact, I'll bring it back out. It says in 2020, it's this. Okay, so this is a little bit off, all right? So the U.S. did not grow as fast as they thought it would, all right? We could talk all day about the reasons behind that, but since this is a math class, I'll not do that right now. But this is the kind of thing that people that are statisticians and do this and work for the government and everything, those are the kinds of things they need to think about. All right. But we at least now know the mathematical side to how they calculate these things. It's now their job to make sure that the formulas they come up with are more accurate. In other words, notice that we just had 2 data points right here. All right. In a real situation, and we don't have time to do that here in section 4.6, in a real situation, though, they would use a lot more than 2 data points, and then that would probably give you a more accurate answer. But we didn't do that here because we're just learning it for the first time, and we just have a limited amount of time to go over this section. So we did a very, very simpler version of what actual statisticians would really do if they were hired by the government to predict future populations, which is an important activity because you want to be ready for however many people. If you work for the government, if you're in the government, you want to be ready for however many people are going to end up being in your country so that you have the correct number of resources for them and you're able to handle that high amount of population that you're going to have. So this is an important thing, but again, this is just a very simple example of what they actually really do, and they would have a lot more data points in order to make it more accurate. Okay, so but this is kind of the basics of the approach that they take, though. Okay, so that concludes Chapter 4 and Section 4.6 in particular. As usual, contact me with any questions or concerns, and you have a good day.